Welcome back to the Deep Dive. Today, we're tackling solids. We're going deep into their structures, bonding, and all those unique properties using Focus 15 from Atkins Physical Chemistry as our guide.
Exactly. Our goal here is to give you a really solid roadmap. We want to go beyond just the definitions and actually show how that tiny microscopic world of atoms connects to the big picture, things like strength, how materials conduct electricity, even their color.
Yeah, and this stuff isn't just theoretical. I mean, think about modern technology. The metals in a plane's engine, those super hard ceramics, the semiconductors inside. Well, the device you might be listening on right now. Their performance hinges entirely on how those atoms are arranged. It really all comes down to geometry.
It does. And what's really neat is how much complex behavior comes from some surprisingly regular underlying structures.
Okay, so let's unpack that geometry. The absolute starting point for crystals is regularity, right? There's this sort of hierarchy to how we describe it.
That's right. First, you've got the concept of the space lattice. Think of it like an infinite, invisible scaffolding. Just points in space showing where the repeating unit, the atom, ion, or molecule sits.
An abstract grid, essentially.
Precisely. And then within that grid, we define the unit cell. Now, this is the smallest chunk, usually a little box or parallel pipehead,
Right.
that if you just slide it around in all three directions without rotating it, you build up the entire lattice perfectly. No gaps, no overlaps.
And these unit cells can be primitive, meaning just one lattice point total if you count up the corners?
Yeah, or non-primitive, where you might have extra points slap bang in the middle, or maybe on the faces of the cell.
Got it. And this leads to the different crystal systems,
Hmm.
like cubic, monoclinic.
Exactly. There are 7 fundamental crystal systems based on symmetry, and combining those with the primitive and non-primitive types gives you the 14 unique Bragg lattices. Knowing which of those 14 basic patterns you're dealing with is sort of step 1.
Okay, here's something that always felt a bit, well, mathematical. Miller indices, the HL of things. The definition is reciprocals of fractional intercepts. Why that specific system? It seems kind of abstract.
It does sound abstract, but it's incredibly powerful. It gives us a unique, standard label for every single possible set of parallel planes cutting through the crystal. So if a plane cuts the axis at, say, half unit along A, a third along B, and 1 unit along C.
So intercepts 12, 13, 1.
Right. You take the reciprocals, 2, 3, 1, and that set of planes is labeled a $31. The real beauty is its geometric meaning. If an index is 0, like $100, it means the plane never intercepts the A-axis. It's parallel to it. It makes visualizing orientations much easier.
Okay. So a 0 means parallel to that axis. That makes sense. And these indices aren't just labels. They let us calculate things.
Directly. They plug right into formulas to find the distance between adjacent planes in that set, the del value. And that distance is exactly what we measure experimentally.
Which takes us neatly into diffraction techniques, right? Using X-rays to actually see these structures.
Precisely. The whole reason diffraction works so well is that X-ray wavelengths are, conveniently, about the same size as the distances between atoms or between those lattice planes. They're on the same scale.
And the core idea is Bragg's law. Lambda 2-day sin theta. Can you walk us through the visual intuition there?
Sure. Imagine X-rays hitting the crystal. Some reflect off the top layer of atoms, some go deeper and reflect off the second layer, the third, and so on. You only get a strong, detectable reflection constructive interference when the extra distance traveled by the beam reflecting off the deeper layer is exactly an integer multiple of the X-ray wavelength.
And that extra path distance depends on the plane spacing and the angle.
Exactly.
Right.
That extra distance is 2 teller sin theta. So only at specific angles synthetal, where 2 teller sin theta equals lambda, the waves add up constructively and give you a signal.
Okay, so the angle tells us the spacing, but what about the intensity of that reflection? What does that tell us?
The intensity is where the real information about the contents of the unit cell lies. It tells you what atoms are there and where they are positioned. 2 key things determine it: the scattering factor and the structure factor.
Scattering factor, that's just about the atom type, right? More electrons means stronger scattering.
Basically, yes. $5 depends on the number of electrons. Heavy atoms scatter X-rays much more strongly than light atoms. Simple enough.
But the structure factor, that sounds more complicated.
It is. Fact atom's a net result of all the waves scattered by every single atom inside the unit cell, taking into account their positions and their individual scattering factors. It's like the combined amplitude from all atoms for that specific EKL reflection.
So it depends critically on how the atoms are arranged within the cell.
Absolutely. And this leads to a really useful phenomenon: systematic absences. For example, in a body-centered cubic A lattice, the atom in the center scatters waves exactly out of phase with the waves from the corner atoms for certain reflections specifically, when 8 plus k plus 8k is an odd number.
So those reflections just disappear.
They vanish. Destructive interference cancels them out completely. By seeing which reflections are systematically missing, we can often immediately tell if the lattice is primitive, body-centered, or face-centered. It's a huge clue.
Okay, so you measure the angles to get the spacings, and you measure the intensities, which depend on the structure factor, if I'm to say so. And you get from that intensity data back to the actual atom positions. I remember something about Fourier synthesis.
Right. In principle, if you knew all the structure factors, both their magnitude and their phase, you could do a mathematical transformation of Fourier synthesis to calculate the electron density, $30, at every point in the unit cell. That map would show you where the atoms are.
But there's the catch, isn't there? The phase problem.
The big one. What we actually measure is the intensity, which is proportional to the square of the structure factor magnitude, allows $2. When you square a complex number, you lose all the information about its phase angle, alpha.
And without the phase, you can't just do the Fourier synthesis to get the electron density map. So how do people solve crystal structures then?
It's a major challenge. One classic approach is called Patterson synthesis. Instead of trying to map atom locations directly, it maps the vectors between atoms in the unit cell.
Vectors between atoms, how does that help?
Well, think about it. The vector pointing from atom A to atom B has a magnitude and direction that depends only on their relative positions, not on where you arbitrarily decided to put the origin of your unit cell coordinate system. The Patterson map plots peaks corresponding to these interatomic vectors.
Okay.
And the height of each peak in this Patterson map is related to the product of the atomic numbers of the two atoms involved. So vectors between heavy atoms give really strong peaks. By analyzing this map of interatomic vectors, which doesn't require the phase information directly, clever crystallographers can often deduce the positions of the heavy atoms first, and then use that partial structure to start figuring out the phases and find the rest.
That sounds intricate. Clever, but intricate.
It is. And there are other methods too, of course. But Patterson was a breakthrough. And before we leave diffraction, it's worth remembering X-rays aren't the only tool.
Right. You mentioned neutrons and electrons, too.
Yeah, neutron diffraction is great because neutrons scatter off the nucleus, not the electrons. So their scattering strength doesn't just depend on atomic number. It can vary between isotopes, and it's really good for locating light atoms like hydrogen, which are almost invisible to X-rays. Plus, neutrons have a magnetic moment, so they're fantastic for studying magnetic structures. Electron diffraction is used more for surfaces and thin films.
Okay, so we've got the geometry, 15A, and how to measure it, 15B. Now let's connect that structure to the bonding, 15C, because that really determines the properties.
Exactly. The type of bonding dictates everything. Let's start with metals. You've got this picture of positive ions sitting in a sea of electrons that are free to move around.
Delocalized electrons.
Right. And structurally, metals tend to pack very efficiently. Think of stacking spheres as tightly as possible. This usually leads to close packing with a high coordination number, typically 12. You get two main flavors: hexagonal close-packed HCP, which stacks layers in an ABA sequence,
Okay.
and cubic close-packed CCP, which is actually the same structure as face-centered cubic FCC, and stacks layers in an ABC-ABC sequence. Both are incredibly dense.
And the electrical properties come from band theory.
Correct. Imagine bringing many metal atoms together. Their individual atomic orbitals overlap and interact, smearing out into a continuous range of closely spaced energy levels that's a band. In a metal, the crucial thing is that the highest occupied energy band is only partially filled.
Meaning there are empty energy states right next door to the filled ones.
Exactly. So electrons need only a tiny bit of energy, like from electric field, to jump into an adjacent empty state and start moving through the crystal. That's why metals conduct electricity so well. There's always an available state to move into.
Makes sense. Okay, what about ionic solids, NaCl, CsCl?
Held together by pure electrostatic attraction between positive and negative ions. No directional bonds, just attraction in all directions. The structure is all about packing ions of opposite charge as closely as possible, maximizing attraction and minimizing repulsion. We talk about coordination numbers, like 1 in all or plus on and dollars.
So for cesium chloride, it's 8 coordination. Each ion has 8 nearest neighbors of the opposite charge. For sodium chloride, it's $6, what determines which structure forms?
Largely the relative sizes in the ions. This is captured by the radius ratio rule. You calculate the ratio, the smaller ion radius to the larger ion radius.
Okay.
For the 8-delenate CSCl structure to be stable, the ions need to be fairly similar in size. Specifically, the ratio Gelman needs to be greater than about 0.732. If the cation is much smaller than the anion, it can't touch all 8 anions simultaneously, and a lower coordination structure like NaCl's, 6-6, becomes more stable.
So geometry dictates the coordination and the strength of these bonds. That's the lattice energy.
Yes, delta HL do. It's the energy change when you take 1 mole of the solid ionic crystal and completely separate all the ions into a gas phase, infinitely far apart. It's a measure of how strongly the crystal is held together.
And you want high charges and small ions for a large lattice energy.
Right.
More attraction, closer packing.
Precisely. High charges and small ionic radii, meaning a small distance dollars between ion centers, lead to very strong ionic bonding and high lattice energies.
But you can't just measure lattice energy in a calorimeter. How do we find it?
We use a clever thermodynamic trick, the Born-Haber cycle. It's based on Hess's law. You construct a closed cycle of reactions, starting and ending with the ionic solid. You include steps like forming gaseous atoms from the elements, ionizing the metal atoms, adding electrons to the non-metal atoms, steps for which we can measure the enthalpy changes experimentally.
Like enthalpy of formation, ionization energy, electron gain enthalpy.
All those. The only unknown enthalpy change in the cycle is the lattice energy. Since the total enthalpy change around a closed cycle must be 0, we can calculate the lattice energy by summing up all the other known enthalpy changes.
Neat. Okay, briefly, the other types. Covalent and molecular.
Right. Covalent network solids are like one giant molecule. Think of diamond-carbon atoms linked by strong covalent bonds in a tetrahedral network extending throughout the whole crystal. That's why it's so incredibly hard. Graphite is another, but with sheets.
And molecular solids.
Those are just discrete molecules like water molecules and ice held together by much weaker forces, van der Waals forces, or hydrogen bonds. They tend to be soft and have low melting points because you're only breaking those weak intermolecular forces, not strong covalent or ionic bonds.
Okay, structure and bonding down. Let's pivot to how these influence macroscopic properties, starting with mechanical behavior, 50D, stress and strain.
Yep. Stress is the force you apply per unit area. Strain is the resulting deformation, like how much it stretches or bends, expressed as a fraction. We distinguish between elastic deformation, where it springs back when you remove the stress, and plastic deformation, which is permanent.
And materials resist these forces differently, measured by moduli.
Right. Young's modulus measures resistance to stretching. Bulk modulus resists pressure from all sides, and shear modulus resists twisting.
And how does the crystal structure tie into whether something is, say, easily shaped like copper versus brittle like zinc?
It comes down to slip planes. For a metal to deform plastically without breaking malleability, layers of atoms need to be able to slide over one another.
Ah, like cards in a deck.
Kind of. Close-packed structures, like copper CCP or FCC structure, have multiple sets of closely packed planes oriented in different directions. These act as easy slip planes, allowing deformation along many directions. That makes copper very ductile. Zinc has the HCP structure. While it's also close-packed, its symmetry means it really only has one main set of easy slip planes, the basal planes. If you try to deform it in a direction that isn't aligned with those planes, it tends to fracture instead of slip, much more brittle. It's a direct result of that ABC versus ABC stacking difference.
Wow, okay. That's a clear link. Now, electrical properties. 15E. We have metals, semiconductors, insulators, based on temperature dependence.
Right, metallic conductors. Conductivity decreases as temperature rises. Semiconductors and insulators, which are just very poor semiconductors, conductivity increases with temperature.
Let's go back to band theory to explain that. Metals have that partially filled band.
Giving electrons plenty of states to move into. Conductivity decreases with temperature because the atoms vibrate more vigorously, scattering the moving electrons and hindering their flow, increasing resistance.
Okay, and insulator semiconductors, they have a full valence band and an empty conduction band.
Separated by an energy gap, the band gap, for conduction, electrons have to get enough energy, usually from heat, to jump across this gap into the empty conduction band.
So in an insulator, the gap is huge. Very few electrons can make the jump. In a semiconductor, the gap is smaller.
Exactly. Small enough that at room temperature, thermal energy excites a measurable number of electrons across, allowing some conduction. And as you heat it up, more electrons get enough energy to jump, so conductivity increases.
But the real game changer is doping, right?
Yeah.
Creating extrinsic semiconductors.
Absolutely. This is the foundation of modern electronics. By adding tiny controlled amounts of impurities, you drastically change the conductivity. If you add, say, phosphorus group 15 to silicon group 14.
Phosphorus has one more valence electron than silicon.
Right. That extra electron isn't needed for bonding. It occupies a discrete energy level, a donor level, just below the conduction band. It takes very little energy to kick this electron up into the conduction band where it can carry current. Since the charge carriers are negative electrons, this is an N-type semiconductor. N for negative.
And if you add boron, group 13, it has one fewer electron.
Correct. Boron creates an acceptor level just above the valence band. It readily accepts an electron from the valence band to complete its bonding, leaving behind a missing electron, a positively charged hole in the valence band.
And this hole can move.
Effectively, yes. An electron from a neighboring bond can hop into the hole, moving the hole to the neighboring site. So it acts like a positive charge carrier moving through the valence band. This makes a p-type semiconductor for positive.
And combining these is how we get devices like diodes.
Exactly. A p-n junction allows current to flow easily in one direction, forward bias, but resists flow in the other, reverse bias. It acts like a one-way electrical valve. And when electrons and holes meet and recombine at the junction, they release energy sometimes as heat, like in silicon diodes, sometimes as light, like in LEDs made from materials like gallium arsenide.
Amazing control. And briefly, superconductors. Zero resistance below tenetrol.
Yes, a truly quantum phenomenon. The key idea is the Cooper pair. At low temperatures, two electrons can indirectly attract each other by interacting with the lattice vibrations, phonons. They form a bound pair that can move through the lattice without scattering off imperfections, leading to zero resistance.
Okay, last couple of sections. Magnetism, 15F. It starts with magnetic susceptibility.
Right. Kate tells you how strongly a material becomes magnetized when you put it in an external magnetic field.
And the basic split is diamagnetic versus paramagnetic.
Yep. Diamagnetic materials have all electrons paired. They're weakly repelled by magnetic fields. Paramagnetic materials have unpaired electrons. These electrons have magnetic moments that tend to align with an external field, so they're weakly attracted.
And paramagnetism depends on temperature, the Curie law.
Usually, yes. For simple paramagnets, the susceptibility is inversely proportional to temperature, Tracto 1Ty, because thermal energy causes random motion, which fights against the aligning effect of the external field. Higher temperature means more randomness, weaker alignment, lower susceptibility.
But sometimes the magnetic moments talk to each other, cooperative effects.
Exactly. That leads to much stronger effects. Ferromagnetism is when neighboring spins spontaneously align parallel to each other over large regions called domains, even without an external field. Think iron, nickel, cobalt, permanent magnets.
And antiferromagnetism.
That's when neighboring spins spontaneously align anti-parallel up, down, up, down. The magnetic moments cancel out, so there's no net magnetization, but there's still long-range magnetic order.
And superconductors have a magnetic trick, too, the Meissner effect.
They do. Type I superconductors, when cooled below their critical temperature titulars, completely expel magnetic fields from their interior. The field lines go around it. It's perfect diamagnetism.
Okay, finally optics, 15G. What happens when light hits a solid?
Excitons.
Right. An absorbed photon can excite an electron from the valence band to the conduction band, leaving a hole behind. This electron-hole pair can actually attract each other electrostatically and move through the crystal together as a sort of quasi-particle called an exciton.
And there are different types.
Broadly, yes. In molecular solids, the excitation tends to stay localized on one molecule, a Frankel exciton. In semiconductors, the electron and hole are often further apart, spread over several unit cells, a Wannier exciton.
How does the crystal structure affect the light absorption? Davidoff splitting.
Yeah. In molecular crystals, the way the molecules are arranged affects how their individual electronic transitions interact. If the transition dipoles of neighboring molecules align favorably, like head to tail, the energy of the combined excitation can be lowered. If they align unfavorably side by side, the energy can be raised. This can cause a single absorption band in the isolated molecule to split into two or more bands in the crystal. That's Davidoff splitting.
Interesting. And what about metals and semiconductors with light? Why are metals shiny?
Metals have that continuum of states in their bands. They can absorb photons across a wide range of energies, exciting electrons. But these electrons can also easily drop back down, re-emitting the light very efficiently, especially from the surface. That's the luster.
And color. like copper being reddish.
That comes down to the details of the band structure near the Fermi level. For copper, there are fewer available empty states for electrons to jump into when hit by blue or green light compared to red or yellow light. So it absorbs blue-green less effectively, meaning it reflects more reedy yellow-orange, giving it that characteristic color.
And semiconductors. Their color depends on the band gap.
Directly. A semiconductor can only absorb photons with energy greater than or equal to the band gap energy, a joule. The minimum frequency it can absorb is 1 Textmin.
So light with lower frequency just passes through.
Exactly. Cadmium sulfide, CDS, has a band gap of about 2.4 eV. This corresponds to blue-green light. So it absorbs blue and green, but red, orange, and yellow light have lower energy frequency and pass straight through. What passes through mixes to look yellow-orange, which is the color we see.
And very briefly, intense light, nonlinear optics.
Yeah, this is cool. Usually the polarization induced in a material is proportional to the electric field of the light. But with really intense laser light, the response becomes nonlinear. You get extra terms, like 1 proportional to the field squared. This nonlinear response can lead to effects like frequency doubling, where you shine in laser light of frequency omega, and some light comes out at twice the frequency, $2. You can turn red laser light into green, for instance.
Wow. Okay, so wrapping this all up,
Yeah.
we went from the basic grid of the space lattice.
Through how we measure it with diffraction, seeing how bonding dictates the main types, metals, ionic, covalent, molecular.
And finally connected all that microscopic detail to the real-world properties we observe. How strong it is, how it conducts heat and electricity, how it behaves in magnetic fields, and how it interacts with light.
It's all interconnected. Every single property ultimately traces back to that fundamental arrangement of atoms and the nature of the bonds between them.
The level of control we now have, particularly with doping semiconductors to precisely engineer electronic properties, is just astounding. It makes you wonder, what's next?
Well, here's a thought. We've gotten incredibly good at controlling electronic structure by swapping out atoms chemically doping. But what if we could gain more dynamic control over the physical structure, the lattice geometry itself, maybe not permanently, but temporarily?
You mean like actively changing bond angles or coordination numbers on the fly?
Maybe. Imagine materials where you could apply, say, an electric field or strain to subtly shift the lattice just enough to perhaps open or close a band gap, or change the available slip planes. Could we create materials that switch from insulator to metal, or from brittle to ductile on command?
Real-time tunable materials based on manipulating the crystal structure itself. That's a fascinating frontier.
The possibilities that open up if we can master structural engineering at that level are really quite something to think about.
Indeed. Well, thank you for joining us on this deep dive into the structure and properties of solids. We really hope this roadmap through Atkins Focus 15 helps you connect the dots in your studies.
And a warm thank you from the Deep Dive team.